Hello. In this video, we are going to derive expressions for the rate of reactions undergoing Michaelis-Menten kinetics. This is a rate scheme that is very common for enzymes, but beware that all enzymes do not necessarily follow Michaelis-Menten kinetics. We imagine that the enzyme E encounters a substrate and it reacts to form an enzyme-substrate complex. And it forms with a rate constant K1. It breaks up back into the enzyme and the substrate without reaction with a rate constant K2. The other possibility is that our enzyme-substrate complex goes on to form a product, and it does this with a rate constant K3. We would like to develop expressions for the rate of change in the concentration of this enzyme-substrate complex. So we have the change in the concentration as a function of time for our enzyme-substrate complex, ES. So notice that we have one way to form ES. The enzyme plus the substrate come together with the rate constant K1. So the rate of formation of the complex is going to be K1 times the concentration of the enzyme E times the concentration of the substrate S. So this is the formation of the enzyme-substrate complex. So it has a positive coefficient, which we leave out there. There are two methods by which the concentration of the enzyme-substrate complex decreases. One of them is this separation of the enzyme and the substrate. So that happens with a rate constant K2. Since it's a decrease in the concentration, we have a minus sign. And then the total rate depends upon the concentration of the enzyme substrate complex, which we have as ES here. So that's one of the means by which we lose the concentration. The other method is that the enzyme substrate complex goes on to form the product. And it does that with a rate constant K3. And the overall rate is K3 times the concentration of ES. We expect that since enzymes are such efficient catalysts that the concentration of enzyme will never be very large, and the concentration of the intermediate enzyme-substrate complex will be even smaller, so we might assume that the change in the concentration of this particular intermediate will be smaller, zero. So here we can apply the steady-state approximation and set this rate of change equal to 0. So here's where we apply the steady-state approximation in Michaelis-Menten kinetics. We can now manipulate this expression, and we get that K1 times the concentration of the enzyme times the concentration of the substrate S is going to be equal to K2 times the concentration of ES plus K3 times the concentration of ES. Next, we can factor the concentration of ES out of the right-hand side. And here we have K2 plus K3. Now if we divide each side of our relationship by K2 plus K3, and just shifting everything to the left-hand side, we get that the concentration of the enzyme-substrate complex is going to be equal to the rate constant K1 times the concentration of the enzyme times the concentration of the substrate, and it's divided by the rate constants K2 plus the rate constant K3. We notice in our reaction scheme that the enzyme can be in two different states. It can be as free enzyme, or it can be bound to the substrate in this complex. That suggests that we can write a relationship for the total concentration, which I'll write as E sub total, and that's equal to the free concentration of enzyme plus the concentration of enzyme that is bound in the complex with the substrate, and that's simply the concentration of ES. We can subtract the concentration of the enzyme-substrate complex from each side to get an expression for the free amount of enzyme, which is going to be the concentration, total concentration of enzyme in any form minus the concentration of the enzyme-substrate complex. Now that we have this particular expression, we are going to substitute our expression for the concentration of free enzyme into our rate constant expression. With that substitution, in for E, and we're just going to move the concentration of S slightly further to the right, gives us a little more room to write. So this is our concentration of the substrate, which was already there. And now we're going to substitute our expression for the concentration of free enzyme, which we're going to write now as the concentration of enzyme total, let's put it as TOT, minus the concentration of the enzyme substrate complex. We can begin simplifying our expression by using the distributive law to multiply out the numerator here. So that gives us K1 times the total concentration of enzyme times the concentration of the substrate, and then minus K1 times the concentration of the enzyme substrate complex, ES, times the concentration of the substrate. And that's the numerator, and the denominator is going to stay the same, which is K2 plus K3. Now we multiply each side of the equation by K2 plus K3, and that's going to give us K2 plus K3 and this is time the concentration of the enzyme substrate complex, ES. And then we get the right-hand side stays the same, which is our K1 times the concentration of enzyme total times the concentration of the substrate minus this rate constant again, K1 times the concentration of the enzyme substrate complex, ES, and the substrate, which is our S. So there we've cleared the denominator from the fraction. Next, we want to add K1 times the concentration of the ES times the concentration of S to each side. And that will give us K2 plus K3 times the concentration of ES and then we add to that the rate constant K1. We're going to make a very small change here. Since the concentrations will commute, let's put the concentration of S here, and then the concentration ES. And then we get to the right-hand side. What's left over is you have K1 times the total concentration of enzyme and that's times the concentration of substrate S. We can factor the concentration ES at the left-hand side, so let's do that. And that gives us the remainder as K2 plus K3 plus K1 times the concentration of S. For our left-hand side. And the right-hand side stays the same as we have K1 times E total times S. Dividing through by the expression in the parentheses, we get an expression for the concentration of the enzyme substrate complex, ES, which is a complicated expression for the time being, which is going to be so we have K1 times E total times the concentration of the substrate, which is S, that's our numerator. And then for the denominator, we have the rate constant K2 plus the rate constant K3 plus the rate constant K1 multiplied by the concentration of the substrate S. The overall rate is equal to the change in the concentration of the product as a function of time. And we know from the second step of our Michaelis-Menten kinetics that this is equal to K3 times the concentration of the enzyme-substrate complex, ES. Now, since we've developed an expression for that, we can simply substitute that into here to get an expression for the overall rate for enzymes undergoing Michaelis-Menten kinetics. The rate, therefore, will be equal to K3 times rate constant K1 times the total concentration of enzyme, that's our E total, times the concentration of the substrate S, and then the denominator gives us the rate constant K2 plus the rate constant K3 plus the product of K1 and the substrate concentration S. So this gives us our complicated expression for the rate of an enzyme undergoing Michaelis-Menten kinetics. We can simplify a little more by dividing the numerator and the denominator each by the rate constant K1. If we do that, the numerator becomes K3 concentration of E total times the substrate concentration S, and then the denominator becomes, we have the rate constant K2 plus the rate constant K3 divided by the rate constant K1 plus the substrate concentration S. And the key to the reason why this is useful is that we can group this particular expression and we assign this a new value, and we call this the Michaelis constant K sub m. With that substitution, we get so the numerator is the rate constant K3 times the total concentration of enzyme times the concentration of substrate, and then this is all divided by Michaelis constant K sub m plus the concentration of substrate S. So this is our initial expression that we've derived. We can now use the expression that we had derived for the general case to look at two special cases. So for this first special case, let us assume that the constant K sub m is very much larger than the concentration of the substrate. If we do that, if K sub m is much greater than S, that means that we can replace the denominator here simply by K sub m. So what does that give us for the rate? Well, it gives us the rate is going to be equal to, so we have the concentration of the enzyme multiplied by the rate constant K3, and we have the concentration of S in the numerator, and then the denominator is simply K sub m. So we see in this particular case, since we can think of K substrate divided by K sub m and E total as constants, that the rate is going to depend linearly on the substrate concentration S. So we see in this case, the rate seems to be first order in the substrate concentration. For the second special case, let us assume that the Michaelis-Menten constant K sub m is actually much smaller than the concentration of S. If it is so, that means that we can replace the denominator here simply by the concentration of S. So what does that give us for the overall rate? So we make that assumption. The rate, the numerator stays the same. We have the rate constant K3 times the total concentration of the enzyme times the concentration of the substrate, and then that's divided by the concentration of the substrate. Notice then that we can cancel the concentrations of the substrate from the numerator and the denominator, and that gives us that the overall rate is simply equal to the rate constant K3 times the total concentration of enzyme. And notice that this rate does not depend on the substrate concentration at all. Therefore, this particular rate is actually a zeroth order in substrate. And this is the situation when the enzyme is saturated with substrate, and this will give us the maximum rate for the reaction. I thank you very much for your attention. This is a very long video. Have a good one.